The path of Comet 3I/Atlas through our solar system has recently become far more precisely understood thanks to a major breakthrough achieved by the European Space Agency. Using highly accurate images captured by the ExoMars Trace Gas Orbiter, TGO, a spacecraft currently orbiting Mars, scientists were able to refine the predicted trajectory of the comet with an accuracy 10 times greater than what had been possible with previous estimates based solely on Earth-based observations. This remarkable improvement is more than just a scientific curiosity. It represents a meaningful advancement in the techniques that could one day help defend Earth from potentially hazardous celestial objects. While Comet 3I/Atlas itself poses no threat to our planet and will never come close to striking Earth, the improved methodology demonstrates how data collected from multiple vantage points across the solar system can be used to strengthen planetary defense strategies. Between October 1st and October 7th, the ExoMars TGO was able to observe 3I/Atlas as it passed relatively close to Mars. On October 3rd, the comet made its nearest approach to the red planet, coming within 18 million miles, 29 million kilometers. This distance, though vast by human standards, is significantly closer than Earth was to the comet at any point during the observation period. Prior to the involvement of the Mars-orbiting spacecraft, astronomers had been relying entirely on data from telescopes positioned on or near Earth. These instruments provided useful, but ultimately limited, measurements of the comet's motion, particularly due to the constraints of observing from a single location in space. Scientists expected that the addition of Mars-based observational data would refine the calculated trajectory, but they were surprised to discover that the improvement was tenfold, a dramatic increase that surpassed all initial predictions. The reason for this massive leap in accuracy lies in the unique vantage point provided by the Mars-orbiting spacecraft. According to the European Space Agency, the ExoMars TGO was able to approach roughly 10 times closer to the comet than any telescope on Earth. Not only was the spacecraft significantly nearer to the object, but it also viewed 3I/Atlas from a different angle than that of Earth-based observatories. This difference in position allowed for highly effective triangulation when the Mars data was combined with data from Earth. Triangulation, a well-established method used to determine the distance and motion of objects, becomes exponentially more accurate when the observing points are far apart. In this case, having two viewpoints separated by tens of millions of miles created a powerful baseline that enabled scientists to calculate the comet's position with remarkable precision. Such improvement makes it possible to better track the comet as it speeds through interstellar space. It is important to note that 3I/Atlas is not an ordinary comet. It is only the third interstellar object ever detected passing through our solar system. Interstellar objects originate from beyond the boundaries of our solar system, traveling through the galaxy until their paths occasionally bring them close to another star. These objects are rare and scientifically valuable, as they represent material that formed under conditions entirely different from those in our own planetary system. The first known interstellar visitor, 1I/Oumuamua, astonished scientists in 2017 with its elongated, cigar-like shape and unusual acceleration. The second, Comet 2I/Borisov, discovered in 2019, provided astronomers with the first close look at an interstellar comet. Now, with 3I/Atlas speeding through our solar system at incredible velocities, up to 155,000 miles per hour, 250,000 kilometers per hour, researchers have another precious opportunity to study the nature and behavior of such foreign visitors. Because 3I/Atlas is traveling at tremendous speed and follows a path that will carry it away from the sun, it will not remain observable for long. It will soon exit the solar system and return to interstellar space, never to come back. That makes every moment of observational time precious. The improved trajectory predictions give astronomers the confidence to aim their instruments accurately, minimizing wasted observational time and maximizing the scientific return. With such precise knowledge of the comet's location and expected motion, scientists can now schedule telescope time more effectively, focus their instruments at exactly the right points in the sky, and collect detailed data on the comet's composition, structure, brightness, and possible behavior changes as it moves through space. Interestingly, the ExoMars TGO was not originally designed to observe distant comets. Its primary mission is to study the thin atmosphere of Mars, particularly by examining trace gases that may indicate geological or potentially even biological activity. To image 3I/Atlas, mission engineers reoriented one of its instruments, the Color and Stereo Surface Imaging System CASIS. Normally, CASIS is used to capture extremely detailed images of the Martian surface, including its canyons, impact craters, dust dunes, ice sheets, and geological formations. However, in this case, the instrument was temporarily redirected away from Mars and toward the stars in order to track the fast-moving comet. This required careful planning, especially as the ExoMars TGO constantly circles the planet, making its orientation in space dynamic and ever-changing. The Planetary Defense Team at ESA's Near-Earth Object Coordination Center played a crucial role in this process. They calculated the exact position and movement of the TGO spacecraft around Mars so that CASIS could be pointed accurately at the comet during the narrow observation window. Observing a comet from a moving platform orbiting another planet is far more complicated than observing it from a stationary telescope on Earth or from an Earth-orbiting observatory, such as the Hubble Space Telescope or the James Webb Space Telescope, JWST. The team needed to compensate for TGO's altitude, speed, orbit, and rotation relative to both Mars and 3I/Atlas. These factors required precise mathematical modeling to ensure that the spacecraft would capture usable images. Another significant achievement of this effort is that the data collected by the ExoMars TGO became the first ever astrometric measurements submitted to the Minor Planet Center by a spacecraft orbiting a planet other than Earth. The Minor Planet Center, operated under the auspices of the International Astronomical Union, serves as a global clearinghouse for coordinates, orbital information, and observational data on asteroids, comets, and other small celestial bodies. Observatories worldwide submit their measurements to the MPC, which compiles, verifies, and distributes the data for use by astronomers, space agencies, and scientific researchers. The submission of Mars-based astrometric data is a historic milestone because it opens the door to future use of non-Earth-based platforms for planetary defense and scientific observation. This development provides an exciting glimpse into the future of solar system science and planetary defense strategies. As space exploration missions continue to expand across the solar system, more spacecraft will be positioned on or near other planets, moons, and asteroids. Each of these spacecraft could potentially become part of a distributed observation network capable of detecting and tracking near-Earth objects, interstellar visitors, and other cosmic phenomena with unprecedented precision. The ability to coordinate observations from multiple vantage points scattered across millions of miles could revolutionize how humanity detects, predicts, and prepares for potential impacts from hazardous space rocks. The success of the ExoMars TGO observation campaign underscores the importance of international collaboration, engineering flexibility, and adaptive mission planning. A spacecraft designed for one purpose, studying Martian gases and surface features, was repurposed in real time to study a fast-moving comet traveling through the solar system. This accomplishment highlights the versatility of modern spacecraft and the ingenuity of mission teams that are prepared to take advantage of unexpected scientific opportunities. By combining data from Earth and Mars, scientists have demonstrated that multi-planet observations can significantly outperform single-point measurements, and that even spacecraft already in orbit can play crucial roles in planetary protection efforts. The story of Comet 3I/Atlas, while brief in its appearance, will likely have long-lasting effects on how astronomers approach the study of interstellar objects and the protection of Earth. The techniques refined during this campaign may prove invaluable when dealing with future objects whose trajectories might bring them dangerously close to our planet. As humanity continues its exploration of the solar system, it becomes increasingly clear that combining resources across planets will help build a safer and more informed future.